So for part A, we know that the capacitance is equal to the electric permittivity of free space times times the area divided by the separation between the two capacitors. So we know that capacitance is inversely proportional to 1 over the separation distance. Again, therefore, if the separation distance was halved, um, the capacitance is doubled. So basically, if d final equals d over 2, then C final would equal 2 times C. Now, furthermore, we know that the potential energy is equal to Q squared over 2C. So we know that the stored energy is inversely proportional to 1 over C. Therefore, if CF equals 2C, that means that the potential energy final is going to equal half of the original potential energy. So if the separation of the if the separation of the plates are halved, so if d final equals d over 2, then potential energy final equals potential energy over 2. So that would be for part A. If the separation is halved, that means that the potential energy is halved as well. And so we can go on to B, asking how much work to actually separate the distance, or rather decrease the distance to d over 2. So how much work to go from d to d over 2. So we know that the capacitance is equal to the electric permittivity of free space times the area divided by d. And again, the potential energy is equal to 2 squared divided by 2c. So at this point, we can say that this is going to be equal to dq squared over 2 epsilon naught a. So essentially, we're just substituting the equation for capacitance into the equation for potential energy. And we know that the change in potential energy is going to equal d over 2 q squared, all divided by 2a epsilon naught, minus dq squared divided by 2a epsilon naught. And this is going to equal negative d q squared 4 times a epsilon naught. So this would be our final answer for the energy needed in order to go from d to d over 2. That is the end of the solution. Thank you for watching.